For
This
joining.
conference will now be recorded.
So I'm going to run through this topic, try and cover quite a number of different subtopics within this to run through what's happening in the press and other parts of the world to set the scene. So we start off with a safety moment, and this is an example of someone attempting to dispose of a PFAS concentrated product via selling it on a website or giving it away free actually on Gumtree. And so this is something we're expecting to see more and more, as it can be very expensive to incinerate these types of foams. But just to be aware that these foams do need to be incinerated, and if they are available for free on websites, that's not really an appropriate use of the website. And we tend to find clients hold these foams, specifically this one, which was stopped being manufactured in 2002 on site in maybe unsecure environments, not quite sure what to do with them for extended periods of time. So we found this pallet about a month ago on a site, which we're now disposing of. So I'm going to run through what's in the news and the media, the chemistry, which can be a bit complicated, uses, point sources, regulations, firefighting foams, how to transition as they are one of the main sources, bait and transport, long-range transport, and then risk management. And then if I've got time, I'll get into remediation. I'm going to go pretty quickly through a lot of slides. So it is a changing world on this topic. We are seeing an explosion of news, especially since 2016 in the US. In Scandinavia, Germany, Australia, Canada, this is also getting more and more attention. So generally, we're seeing more interest in products, and these can be PTFE, Teflon, firefighting foams, and components of consumer products like pizza boxes. But the thing that caused alarm to start with in the US was this Hoosick Falls supply in 2016, with the water supply being shut down and the governor setting up a short-term health advisory of 100 nanograms per litre. So following that, there was some political pressure put on in 2016 across the US, and the US EPA set up this long-term health advisory of 17 nanograms per litre of PFOS, PFOA, and that immediately put around 6 million Americans' drinking water supplies out of compliance. Therefore, as a result of that, people were put on bottled water until the supplies were fixed and brought below the standard. And since then, it's sort of catalyzed. So there's a lot more attention to this topic. So we've got feature films currently around. Amazon has got some Dark Waters on that hit the movies in the UK. I was in Edinburgh at the premiere. We're seeing more and more come out. Gen X Chemical Cocktail is another film that's out. The Devil We Know is on YouTube, which is more of a documentary of the Parkersburg story, which is the focus of Dark Waters. And Erin Popovich is tracking this and supporting legal cases and talking to communities globally. So there's more and more press on this topic. It's hit Europe, yeah, certainly in the Netherlands. Last September, October, there were some strikes by construction workers as a result of regulatory standards being pretty low, and they've been unable to move soil. They marched to The Hague to protest on this topic, and there was an aim to relax the rules, and new limits came out, I think, about 2 months ago now. So it does show how regulatory standards need to be set to be not below background state, and that needs to be considered to be important. So the chemistry of these compounds, they are pretty interesting. They tend to be highly mobile. The shorter chains we go into are more mobile. They tend to travel, especially in water. They're soluble in water, but they also persist on sites for extended periods of time and act as continuing sources. They show no real sign of environmental biodegradation and have been termed forever chemicals. I mean, all halogenated compounds are not electron donors. They're not going to be used as an energy source by microorganisms, full stop. So in an aerobic environment, they're not going to degrade. We do see some degradation of chlorinated compounds, but not fluorinated compounds. Surfactants, yeah, they are surfactants. They're surface active agents, and they stick on interfaces and surfaces, especially at higher concentrations. The longer chain ones are known to be more bioaccumulative than the shorter chain ones. So they biomagnify up the food chain, and they concentrate, especially in human blood, more so than, say, monkeys, mice, rats, etc. We have a 4-compartment kidney so we can absorb and retain these for longer. We get an upper concentration. And there's more and more information on toxicity, and that's mainly focused on the two main compounds of regulatory concern, which have been PFOS, PFOA, but there are more and more publications coming out on the other compounds, some which bioaccumulate more than others, and some bioaccumulate in plants, and we've got more complex chemistry to understand. So we talk about PFAS and PFAS, and that's per and polyfluoroalkyl substances. So there's two main types. And what we used to talk about were PFCs and PFOS, PFOA. So these are perfluoroalkyl acids, they're the per type. And PFOS, PFOA are the 8 carbon long compounds where you've got octanoates, so PFOS is octane, but we also have homologues that are shorter and longer chain. And this means there are multiple PFCs out there. And we also have PFCs that don't have carboxylate or sulfonate groups on, that could be phosphinic, phosphonic acids. And the new perfluoroalkyl acids are the ethers with oxygen in the chain as well. So they tend to be some of the replacements we're seeing for industry. But all of these resist biodegradation totally. There's no mineralization seen. They are ultra persistent in the environment and they can travel. So the polyfluorinated compounds tend to be precursors to the perfluorinated compounds. So we have, for example, on the top right, this is a fluorotelm alcohol. It's volatile. It doesn't have a polar functional group. It evaporates. It will move into the atmosphere and UV light will cleave off these hydrogens. Bacteria can also attack these hydrogens as a food source, but this is then a precursor to PFOA. So we have some volatile PFASs which hit the atmosphere and PFOA can come back down in rain. It's the same in firefighting foam and many other products. We have a perfluoroalkyl group as part of the molecule, but the rest of it is going to be biologically attacked to degrade, to form or transform to form a perfluoroalkyl acid. But you don't necessarily have an analytical standard to be able to detect these, and they have different fate and transport properties. Especially the cations in some foams like these will stay where they are, and the zwitter ions will stick on the soil as a longer lasting source of a perfluoroalkyl acid. So to try and make that simpler, we have the PFCs, which are now termed perfluoroalkyl acids, and that's PFOS, PFOA at multiple chain lengths. We have the precursors, which biologically transform to make the PFAS, which we tend not to be able to detect directly until we've got an analytical standard. And these are transformed through, so the non-fluorinated part of the molecule will be attractive to an organism, or UV light can attack it, and then you'll get the formation of what are more commonly regulated, the PFAS. So it's this perfluoroalkyl group, which is extremely stable. There's the strength of the carbon-fluorine bond and the shielding of the carbon-carbon bonds by the molecular size of the fluorine means that it's pretty much impermeable to attack by oxidants, reductants. Even if you do a chemical oxidation test, a COD, these are not picked up. Oxidants do not attack these molecules very well at all. So, meaning it confers extreme persistence to the molecule, but the rest of the functional group can mean you cannot necessarily detect it. So this means we've got multiple types of sources, thousands of precursors, and they aerobically transform through, it's more quickly under aerobic conditions to form the perfluorinated compounds. Now the analytical tools are out there, maybe are hitting the tip of the iceberg of the PFAS mass that's there, but then it does depend on what's regulated and what's known about the compounds that are regulated in terms of toxicity, so they are regulated. So we've got different methods out there, like 537 is being replaced. They're up to, well, the last we saw 65 individual analytes that have analytical standards, but that list is growing. And you're basically not really measuring the total mass, and that may affect how you derive a conceptual site model. So there's more methods coming out, and the total oxidizable precursor assay, it was used in the UK first commercially. That's back in 2015, and we've got extractable organic fluorine, we've got PIGY, particle-induced gamma emission, we got high-res mass spectrometry. So top assays now commercially available. There's a few labs doing it. I recommend ALS. We've been working with them for now 5 years on this. Extractable organofluorine ion chromatography. This burns a sample and you measure the fluoride coming off. Detection limits aren't that low, about 2 ppb. And PIGGY is more for surfaces, where you can detect PFASs on the surface by you shoot a proton at it and you see the gamma coming off, and that indicates how much fluorine's there. So it doesn't identify any PFAS individually. And the high-res mass spectrometry, more analytical tools that are used by academics, and that is used for more forensics work to work out which product comes from where. So the top assay uses an oxidant to mimic what the biology does and converts precursors to perfluoroalkyl acids, and then you measure the perfluoroalkyl acid indirectly because you don't have an analytical standard for this molecule, and you look at before and after the digest to look at how much precursor mass is there. If we look at this on some foams, we have some older foams like the 3M Lightwater product made by electrochemical fluorination, and then newer foams, the fluorotelomere foams. You just do standard analysis, you do not find the standard analytes in the newer foams, and there's a certain amount of PFAS in the old foam here. But when you do an oxidative digest, you can then see that there were PFAS in there, you just don't have analytical standards for them. So it's a way of detecting indirectly the precursors and getting an idea of their chain length. And it's also, you can see here, there's a lot of C6 in this as well, and that is the C6 sulfonate. So even though this is PFHXA, yeah, there are some slight changes in the top assay compared to the biological transformation, but you can work around that to work out what's there and the risk it may pose. So PFAS manufacturing, it has been used in so many different places, like firefighting foams, definitely chrome plating, metal plating, textiles, any garment you've got that has an element of water and oil repellency, not just Gore-Tex. Any performance fabric likely has PFAS on it. Small electronic components have PFAS in. Photolithography, definitely PFAS, paper coatings, paints, hydraulic fluids. So many uses. Three main manufacturing processes. ECF tended to make the sulfonates. This was licensed by 3M. And this makes some PFOS, PFBS, for example. You tend to make branched and straight chain with this, so you tend to have a branched straight chain ratio of 30 to 70, 30% branched. Fluorotelomers tend to make just straight chains, and they tend to be units of 2 when they're made, so 6, 8, 10, etc. These are what is used to make the current foams. And then the newer process is oligomerization that's used to make the perfluoroalkyl ethers. So we've got a general shift away from one process to another. Yeah, many products like dyes, adhesives, wax, even car wash waxes, etc. Three main types of foam. We've got aqueous film forming foam, film forming fluoroprotein foam, and then a fluoroprotein foam. So anything fluoro in a foam will have PFAS in it. But when it comes down to point source contamination, when we start thinking about conceptual site models, we're thinking about fluoroplastics and construction, or paper mills, carpet and textile manufacturing, metal plating, paint manufacturing, car washes, leather tanneries. And then anywhere that's doing or has done fire training historically, or is still doing fire training using more modern foams that still contain PFAS. Wastewater treatment plants tend to concentrate PFAS into the biosolids, and then there can be various disposal routes for biosolids, where they can be put into a hole in the ground or can be spread on fields. So that can be a potential source of issue in terms of setting up some kind of pathway for contamination. And landfills, yeah, we've got so many consumer products that landfills tend to leach out PFAS. There are many more products being formed, so this is a good summary of the next generation, and we're still seeing them used widely. So toxicology and regulatory issues. The toxicology work is still ongoing, I'd say. There are various studies out there. For the longer chain compounds, there's more of an issue with PFOS and PFOA, that they bioaccumulate in people specifically, and PFHXS has a longer half-life in humans with 8.5-year half-life. Exposure tends to be via ingestion, not skin contact, and drinking water and food are the main sources of exposure. And we can pick out drinking water here as if you're drinking 2 liters of water from your tap every day. This is where we get very low drinking water standards derived. But you can also get ingestion from household dust. So there are also consumer products out there that contain PFAS. So toxicology is certainly moving forward, and various epidemiological studies are now being used to inform guidance. This has meant that what tox data underlies the drinking water standards is coming down and down. So we're seeing tolerable daily intake levels being proposed by various regulators which underlie how we interpret drinking water standards. And we've gone from EFSA numbers back in 2008 of like 1500 to what's being proposed here, where we're up to 0.8. So we're seeing a general decline, meaning regulatory standards, especially focused on drinking water, become much lower and lower. So globally, that means we're seeing very, very low standards being promulgated for multiple different PFASs, where in the States, federally, it went to 70 nanograms per litre for PFOS, PFOA. Other states have instigated lower standards for more PFASs. So Vermont covers 5 PFAS at 20 nanograms per litre. The lowest I know, for example, is Denmark, which is currently considering 3 nanograms per litre for PFOS, but they've got 100 nanograms per litre for a sum of 12 compounds. So we're generally seeing much lower standards than are currently used in the UK, where we're still relying on the EFSA 2008 TDIs. The rest of the world, Canada, various states across the world, in terms of US states and states in Australia, have gone much lower. Australia is at 70 nanograms per litre for PFOS and PFHXS combined. And we're seeing adoption of the top assay as well, especially for firefighting foam analysis, but Queensland regulators are using top assay to verify remediation. So we are seeing advances in understanding of this issue. There's also exposure when you start to consider perfluoroalkyl acid and precursor exposure and transformation in vivo. That means there's some direct and indirect exposure when you're considering ingestion. And we move back to the POPs. Like PFOS was listed as a POP, but these tend to be historically chlorinated compounds. And what we're seeing now is PFOS, PFHXS, and PFOA being listed, but the criteria under which they're listed are persistence, bioaccumulation, and toxicity. And the thing that's affecting this now is that the criterion that may be becoming more important to protect drinking water supplies is mobility. And these chlorinated compounds are not very mobile, so they tend to stay in source areas. And what we're seeing with replacement compounds is to protect drinking water supplies, the mobility is being considered by regulators because the short chain compounds are more mobile, they travel further, they are replacing the longer chain. So we get C8 foams that are replaced by C6. And there are various intermediates in this transformation which are showing that they are bioaccumulative. So the German regulators and Europeans are pushing a persistence and mobility as criteria to regulate chemicals, to try and focus on drinking water supply protection, as opposed to keeping chemicals out of the food chain. Where you've got something mobile, the pathway tends to be a drinking water led one, which is completely logical, as then the mobility is more important than the bioaccumulation. So for drinking water quality, PBT, persistence, bioaccumulation, toxicity, is perceived to be only marginally effective. And it protects the drinking water, doesn't protect the drinking water supply, it protects the food chain. So this is really the focus of what we're seeing in regulations that are coming out of Europe, with various criteria, very persistent, very mobile, for example, and PMT. So that seems to be focused on short chains, which tend to be lesser regulated than long chains, and they are the replacements, and they're still in use. But there are certainly uncertainties with regard to exposure, toxicity, bioaccumulation, but they are extremely persistent and they are highly mobile. So firefighting foams, quickly just run through these as they are some of the major sources. We see an evolution of firefighting foams from AFFF, FFP, FP to fluorine-free foams, which are performing extremely well now. So more and more movement towards fluorine-free foams in the world. Definitely what we're seeing in Australia and the States, Canada, there's a definite move towards fluorine-free. So 3 types of foam that contain PFAS, used since the 60s onwards and still in use today. C8, PFOS, PFOA, being phased out, but still is present in some foams, or maybe historic foams still stored on sites. Shorter chains being used, less bioaccumulative, but extremely persistent and more mobile. And now we're seeing more regulations with PFHXA, the focus of ECHA regulations. And there's at least some proposals came out late last year to restrict precursors to PFHXA, which covers C6 foams. The C6 foams tend to have multiple types of precursors in, like this molecule, which transform through to make something called 6,2-FTS. We can see the formation of the 5,3 acid in this formation, which is bioaccumulative in rats, and 6,2-FTS is showing it's bioaccumulative in marine invertebrates. But then we get a spectrum of different perfluoroalkyl acids, which these are the compounds that tend to last forever in the environment and are commonly being regulated. But we are seeing 6,2-FTS being regulated in Canada and parts of Europe as well, sort of Sweden, Switzerland, etc. Regulations on use of firefighting foams are just rapidly expanding. This is all like 2018 to 2020. All these states are starting to restrict use of firefighting foams, and this is moving very quickly. Yeah, regulation of PFHXA through ECHA. It's a proposal to restrict the use of PFAS foams and start adopting fluorine-free, which is being pushed through. And at the same time, there's been research work over the past 4 or 5 years via last fire trials to show that fluorine-free foams are very effective, with successful extinguishment of this 40-meter-long fire at Dallas-Fort Worth Airport back in 2018, and plans for many further trials with them. They're building a new fire testing area in France that's larger than this. So we're seeing real-world fires being extinguished with fluorine-free now. Adoption of fluorine-free with Danish Defence, they're very positive around the use and adoption of fluorine-free foams. Some of their trials and their testing, they're basically saying they would trust their life to these foams if they were stuck in an aircraft. Seen oil and gas companies in Scandinavia, Equinor, formerly Statoil, shift their whole portfolio to fluorine-free. And now we're seeing independent certification of what's in fluorine-free foams in terms of their environmental profile, and green screen certification coming in to demonstrate that there are no particularly toxic or persistent compounds in the fluorine-free foams. They're not going to form a future environmental liability. We're also seeing when we swap out foams that if you wash them out with water, you get rebound into your fluorine-free foams. So this foam in Australia ended up starting off as a fluorine-free, but after it had been in the suppression system for a couple of years, it rebounded to 1.6 grams per litre of PFAS, which means it's now classed by the regulators to be a persistent foam again. So decontamination of fire extinguishment systems can be very important. And we've shown that water is not effective. This is a sequential trial where we tried it in a sewer to start with. We used caustic to clean the scum off the sewer. And water wasn't really pulling anything off the surface until we used a cleaning agent we developed, which pulled the mass off. And then we've also shown that really you need to be verifying that this works using top assay. So the difference between not using top assay and using top assay can be very significant, like orders of magnitude difference. So we're currently using this cleaning agent widely in Europe and the States and Australia to clean out fire suppression systems. Disposal of foams, these HFFP foams cannot be treated biologically, so they can't go to treatment works. If they go to sewage treatment plants, there will be no treatment that's effective, and there'll be concentration in the biosolids. So we're now seeing more attention to incineration in the US, with the US Air Force stopping incinerating foams as a result of recent concerns with emissions, and there needs to be a route of disposal. So there's an active area of research for disposal of foams. Yeah, incineration is more of concern with release of things like carbon tetrafluoride, which needs some 1400 degrees C for it to be destroyed, whereas the PFASs, there tends to be literature showing it's around 1000, 1100. So we're seeing more use of cement kilns as well, especially in Australia, to take the waste, which is another market. Then various foam treatment options. We're using ultrasound and successfully degrading complex waste at the moment, but it's still at a small scale. Some of our data on PFAS with the fluoride mass balance that got published about a month ago, and some more work we've done on complex wastes where we've successfully treated PFASs using ultrasound. So fate and transport, this can be complicated, but in general, we have multiple different exposure routes and transport around because there's no biological attack on these molecules that's meaningful. You may get transformation of one to the other. And so we're seeing exposure routes coming from like air emissions from landfills, certainly landfill leachate getting into surface waters. But it does tend to depend which is posing the most risk. And out of all of these, it tends to be drinking water that is the most potential, this most sensitive pathway to cause harm. We've got atmospheric deposition coming from biosolids coming off land, wastewater treatment plants and landfills at low rates, but also production plants with long-range transport. And there's a greenhouse effect of these things evaporating off and concentrating at the poles. In terms of rivers that are contaminated, this is a study done by some Chinese researchers, and the Thames came out as the highest in these rivers here. These are lakes. So we're also seeing the new emerging replacement compounds turning up in rivers. So we're seeing a general increased concern and more focus on the research, where researchers are finding PFASs in multiple matrices rivers around the world. There was some work done by the Environment Agency back in about 2008, where they looked at lower and higher risk sites, and they were finding reasonably high concentrations in various aquifer types. So we certainly have concern in the UK. We've seen the River Severn that reported to have 238 nanograms per litre flowing at 33 cubes a second. And we compare that to the European EQS at 0.65 nanograms per litre as an annual average. And there has to be a reality that we are way above that in many rivers. And whether that's achievable is a question. So this is a recent report that came out showing EQS exceedances and locations, and you could identify potential sources as a result of these. So movement of PFASs in groundwater in dilute plumes tends to be focused on interaction with the fraction of organic carbon, and you get, as with many other hydrophobic contaminants, you get retardation as a result of this. That dominates long chain fate and transport, but for the shorter chains that don't have a hydrophobic tail, it tends to be an ion exchange process, and so you can see they move further, but you can have them more of an effect on retardation as a result of the nature of the mineralogy, and interaction more with positively charged minerals will cause sorption. So in general, short chains move further than long chains. Then in terms of soils, we started using top assay to identify the mass in sources, and this is some data from a site where we see the unsaturated zone soils tend to be more highly impacted than those in the smear zone here. And I think the reality of where we are now with this is the extraction techniques used to extract the PFASs that are precursors to these compounds are now shown to not be really effective. And so a recent publication showed we're missing 97% of the mass of PFASs in source areas because the extraction techniques are not appropriate for these. So this is just a fraction of what's actually there. And in some foams, like the older ECF foams, they tend to be high percentages of cations and zwitterions as precursors. And then it's what risk do these pose? And they are going to transform to produce things like PFHXS. But it's then, where are you going to put this soil after you've done treatment or remediation? And is there a residual risk associated with these bleeding off these fluoroalkyl acids? So certainly a lot more active research being done, and analytical tools in the commercial arena for soils not being perceived to be 100% effective. Yeah, in soils, this is a plan of the concentration of PFASs in soils with chain length. And in general, we tend to see over a 2-meter profile. The longer chain PFASs stay at the surface much more, and the shorter chains move through. So they do tend to stick together and form layers on the surface. So if you put all the elements of a conceptual site model together, we start to think about a fire training area. We've got hydrocarbons, which tend to be lost to ground, and PFASs. When we did our work at Bunsfield, we just focused on PFOS. That was back in 2005, and now we're sort of thinking about, well, Do we need to look for shorter chain compounds? Are they posing a potential risk? What are we being asked to look for? But they will travel further and they're more mobile. But then we've also got some anionic precursors which are mobile, and they tend to be more mobile than the corresponding perfluoroalkyl acid. And they also potentially have these new foams have precursors in. So we then have a source zone which tends to be anaerobic with cations in it, and that can be an ongoing source of PFASs. So the hydrocarbon plume will enable really the formation of a pretty short sort of 100, 200 meters of groundwater, which can be anoxic. And so the next consideration is, once you move back into this redox recharge zone where it becomes more aerobic, do you then have transformation of your precursors to your perfluoroalkyl acids? And do you really know what's happening on your site if you don't look for precursors? Because you could be seeing all of a sudden something turning up here, and it could be coming from precursor transformation, as opposed to thinking you're another source. It's more complicated. So long-lasting sources, a couple of publications showing, soils can be sources of PFASs for 20 years or more. We're seeing publications predicting concrete can be PFAS sources for 100 years or more. So there's certainly concern over how you do analysis, that the soils are a continuing source. And when you start looking for source areas, this publication showed that fundamentally you would have missed a source if you hadn't used top assay. There was a separate source here of precursors bleeding off. And basically, if you're going to try and identify source areas, your CSM could be wrong if you haven't looked for sources using top assay. You could miss a source of proprietary precursors which are bleeding off towards a plume if you don't use top assay. So point source management and the pragmatism of commercially managing these, we really need to be looking at source pathway receptor linkages. Some of these sites may be source pathway receptor linkages, some may not, depending on the site setting and the amount of PFAS lost to ground. Firefighting training areas, there was a deposition of PFAS on the ground continually, usually potentially to open ground or maybe towards a wastewater treatment plant that bled from the fire training area. Both we see quite commonly. With the amount of mass that's thrown on the ground deliberately there, they tend to be showing a higher potential to produce a source pathway receptor linkage. Some of these other sites may be source pathway receptor linkages, they may produce a risk. And then some of these may just contribute to diffuse and background where there's no real risk being posed. So there has to be some pragmatism in managing these sites. We tend to be using GIS vulnerability tools and basically multiple different tools to look at these. We are seeing excessive costs being proposed in countries where risk-based contaminated land management is not seen. You're trying to get to a drinking water standard in groundwater. We're seeing this soil exchange talking about 1 to 3 billion euros and remediation at Dusseldorf Airport, potentially reaching 100 million euros. So there really has to be some pragmatism when we start to look at managing PFAS source zones. We've done a lot of work on a few sites. One of the sites we're still working on is Channel Islands in Guernsey, where we looked at an airport which was at the top of a hill with a drinking water reservoir down the side of here, and evaluated very quickly where the sources were and worked out which ones were bleeding off to the reservoir, and then basically isolated those soils and put in a water treatment system. So a lot of the work was around modeling and understanding the interaction with the soil, the groundwater, leaching to surface waters and dilution into the reservoir, in order that we could then derive site-specific target levels for the soils. And this was done via a linkage model where we looked at calculating the attenuation among all these potential pathways. And we've certainly been able to bring the levels down. And at the moment, we're working on what to do with the soil that's being stored. So treatment and restoration. We put this together in a publication back in 2018 to try and show there's a lot of experimental technologies out there that we're also seeing a lot of things that maybe aren't going to be practicable. So we're seeing activated carbon being used, ion exchange. Generally, activated carbon is better at longer chains, and ion exchange can come in for short. But we see foam fractionation various other technologies are evolving and becoming more commercially available. And the same for soil, where there's more and more technologies out there, but they're still experimental. So activated carbon can be effective, but it's really got more of an issue when you've got high TOC, and that can cause problems where the carbon is consumed as a result of the other organics in there. And it's not particularly effective on anionic precursors or on short chains. So if you want to be more comprehensive, we're seeing the use of ion exchange resins. This is just showing the breakthrough of some shorter chains, which happens pretty quickly. And then when both vessels are replaced, we see the short chains coming back through again. So limitations with both the precursors and the short chains with using activated carbon. New reagents that are out, I think, and reagents that are being used, we're certainly seeing injection of carbon products into the ground, and there are concerns over their distribution. And there's some key questions around how long they will last, how well they distribute, and they don't have any mechanisms for biodegradation when you're considering PFAS. So are they making a secondary source? Then we move into ion exchange resins. They are being used more and more frequently, and they could take out a spectrum of PFASs. So short and long chain. So this is what I'm seeing being adopted more and more, but there are plenty of new resins and materials being made. So we're seeing adoption of novel functional groups being attached to various scaffoldings, which are then being used to selectively or specifically remove PFASs via ion exchange, or what's termed a fluorophilic effect. Then as far as designing this, what we've been doing is working with an HRX well, which is a large diameter horizontal well that's installed along the length of plumes and focuses groundwater from a wide area into a permeable pathway to go through a treatment media. And we've also got ultrasound in here at some sites and various different treatment media. And this is actually showing a very high capacity to funnel groundwater through a media. And we've got cartridges in here which can then be removed. So we see the concentration going down over time, and it's more of a passive in situ remediation approach that can be engineered. So several projects in the US and now in Europe are moving forward using HRX wells. And we do a lot of modeling around this to show that this passive approach is effective in your lithology or in the lithology of the site to make sure it will actually work. So fixation, tends to be around soil stabilization, which is a pragmatic approach to remediation of PFAS source areas. It's just concerns over long term, and the PFAS are still there, and will they eventually leach out, or will the solidified stabilized mass break apart? So we've run a trial now. We're into 3 years of testing various reagents and using the leaf method, and we got in situ trials as well. So this is the trials in the lab, and we got field scale trials with wells drilled showing that we're not seeing PFAS remobilize now after 3 years. So stabilization is one option, but it does depend upon the use of the site and the perception of risk, and whether there's a need to physically remove the PFAS or treat them. Destruction is difficult. I'm involved with a project with CERDIP in the US, where we're working with Peter Jaffe on this organism, which did show some good results at potentially attacking PFAS. So I think it's early days with this to try and work out what's happening in these growth media. So there would be huge potential if there was an enzyme that could attack PFAS, but I'd say it's very much early days at confirming that this data is real. Electrochemical degradation we're seeing being produced as a technology at a small scale. It is showing good results, but I think the main concern here is if you've got any chloride or bromide also in the water, you will make bromate or perchlorate, and so you will need a secondary treatment process to deal with the perchlorate formed. And so there's more concern with this technology when you've got water with any chloride or bromide in it. Ultrasound is being scaled up at the moment. We are seeing great results with destruction using this, and it's certainly able to degrade the PFAS, and we recently published a paper talking about the mechanisms and it looking like it's not thermal. in that you do get very high temperatures which aren't transmitted to the main body of the liquid, but it looks like it's potentially a chemical attack method with a solvated electron being used. This tends to work by creating pressure waves, and you get expansion and compression, and the bubbles create extremely high temperatures and plasma, and it looks like it's the plasma that is destroying the PFAS. This is a nice mass balance of PFAS, which is one of the most recalcitrant. The sulfonates tend to be more recalcitrant than the carboxylates, so this is a nice example of breakdown of PFAS and accounting for all the fluoride that came off it. And the concentrate, also this complex waste we've worked on. So we've got multiple projects now where we're working on innovative research for CERDIP and ESTCP. I think we're up to about 12 at the moment, which have all been approved, and I'm involved in 4 of those. And as a summary of quite a lot of information, long chains are being replaced by short chains of ethers. Precursors form PFAS. There's a lot more regulations and political attention, community attention, lawsuits, and portfolio assessment may be useful to consider the risks if clients have multiple sites. There's long-range transport mechanisms, so there are background concentrations out there, and CSMs are going to be absolutely essential to determine the risks posed by PFASs to make sure that there's an appropriate amount spent on trying to manage their cleanup. We don't have a biological M&A sort of approach necessarily here. We do have dilution and attenuation, but there's no sort of biological attack. And there's a significant mass of PFAS in source areas, and a lot more mass than we thought, which can be bleeding off for decades. And I think as we move forward, we're seeing an increasing number of regulations focused on replacement compounds. So as opposed to what is regulated today, there's an ongoing risk of what may be regulated and is likely to be regulated in the next few years, and on what firefighting foams are being used, and what's going to cause a potential future liability. So the work we've been doing, there's a 204-page chapter that took a lot of time to write in here. It's Emerging Contaminants Handbooks on Amazon, and we put that out early 2019. We've got various books we've written on remediation engineering. The Concava report's available online. That was a pretty comprehensive review of the properties of PFAS, and that's now 5 years old. Various other publications on top assay and what it means. This is a free download review of emerging technologies that we put out back in 2018. We got mentioned in this Fluorine Detectives article in Nature, which is a great summary of this issue to send to people. Really well written. The Clare guidance, Jake Hurst and I put that together. It got published about 18 months ago. And more recently, articles in Airport Review as we start to see the adoption of fluorine-free foams and environmental liabilities being realized with regard to ongoing use of PFAS and legacy use of CA compounds. This is about a month old, with the concerns over air emissions and byproducts as you try and destroy PFAS. There's more concern with thermal expansion of liquids and the ability for them to be incinerated as opposed to solids. So that's certainly mentioned in there. And this is about a month old. The catalyst, and there's a pretty long summary of regulations. And there's one more that's not on here, which is a analysis paper that's just been published in the past month. So that's it. Sorry, that was a quick run through of a lot of topics, but hopefully that stimulates some questions.
Thank you so much, Ian. I know that you had promised a quick run through, but that was exceptional. And I know that it's a huge topic, and you've done absolutely brilliantly to give a bit of a taste for all of the different elements of looking at these substances in the environment. I'm just going to stop recording now.